Welcome to Teja Statistics. In this class, we are going to discuss about the uh, theorems in semester 5. Very important theorems. Prove that variance of y bar of st of naments is always less than or equals to variance of y bar of st with proportionality less than or equals to variance of y bar of r, that is random sample. So let's see the proof here. Proportional allocation is a simple random sampling. So to make comparisons, we are going to use the variances. So proportional allocation versus, first of all, simple random sampling we are checking. Okay, we have variance of y bar of st with the proportionality 1 divided by n small n minus 1 divided by capital N summation I runs from 1 to k of pi of si square, and variance of y bar of r, that is denoted with a simple random sampling value 1 divided by n minus 1 divided by capital N of s square, where s square is the sample variance or population variances. So in order to compare, we shall express s square in terms of capital Si square values. So what is this s square? Is the sample mean square values. uh, we have s square formula, or if you compute with capital N minus 1, then it is said to be the population. Okay, s square formula is equals to 1 divided by n minus 1 summation I runs from 1 to k of j equals to 1 to n ni of the formula yij minus y bar of ni plus y bar of capital Ni minus y bar of n whole square. So if you do the cross multiplication, then you can expand this a plus b whole square formula. So you can take yij minus y bar of ni as one term, and y bar of ni minus y bar of capital N is another term. So n minus 1 into s square is equals to double summation of this expansion. Next, to see the independent term is going to be the 0. So I runs from 1 to k, j runs from 1 to ni of a square plus b square. In that format you express these terms, and applying the summation over here, I runs from 1 to k. This capital N minus 1 of si square is equals to summation I runs from 1 to k of ni. So if you remove the capital N value, then with the summation y bar of ni minus y bar of n whole square. So a square plus b square format. If we assume that ni and n are sufficiently large so that n minus 1 and n is both are equal, ni minus 1 and ni is also be the equal. So capital N is n square is approximately equals to the summation I runs from 1 to k of ni si square plus summation ni of ni y bar of ni minus y bar of n whole square. So this can be written by, or the converted the formula into the proportionality ni divided by capital N. So si square is approximately equals to the value. So here now we are comparing this s square in terms of the variance of y bar of s square formula. So on comparing this with the another value 1 by n minus 1 by capital N of summation I runs from 1 to k pi of si square plus pi of y bar of ni square. So we got the value that is only here of in the terms of s square, the above. So hence we can see, so multiplying the value into the each and every term, then variance of y bar of r is approximately having equals to the value of variance of y bar of st with the proportionality plus some non-negative quantity, so which is a very greater here. So uh, if you are adding that value to the proportionality, then only you are getting the random in the sense. So which one is greater? So variance of y bar of r is always greater. So here they put it as equation 1. Now we are trying to compare the Neyman allocation versus the proportional allocation. So Neyman allocation is different and proportionality. What is the proportionality? Capital N Ni divided by capital N. The Neyman allocation is you can see we have variance of y bar of st stratified with the proportionality. We have the formula. So optimum allocation, Neyman optimum allocation, we can say that. So we have the formula with the pi, so 1 divided by n summation pi of si square minus 1 divided by summation pi of si square. So here is a small n and here is a capital N. Now variance of y bar of st of proportionality minus variance of y bar of st of optimality. If you do the subtraction, then you will get as in the form of some terms getting cancelled here. 1 divided by n, if you do the common, then summation I runs from 1 to k of pi of si square minus summation pi of si whole square you will get. So here this s bar formula, what is s bar? Summation uh, or s, we can say that summation I runs from 1 to k pi of si. So 1 divided by si 1 divided by n into summation I runs from 1 to k pi of si square minus s square you are substituting. So here s bar formula you are writing. So then which is be the a positive quantity, whole square is always be the greater than or equals to 0. Hence variance of y bar of st is a minus variance of y bar of st with the proportionality and optimality is always greater than 0 you got. So which is greater here? The proportionality is greater. The very least value is the optimum allocation 2. So put it as equation number 2. Now Neyman allocation also known as the optimum allocation. Now Neyman allocation versus simple random sampling. This is the last extension of the theorem. So we have in first part variance of y bar of r is approximately equals to the variance of y bar of st plus with a proportionality of some non-negative quantity. Put as equation star. Now from that second part, so what we are observing that variance of y bar of st with the proportionality minus and variance of y bar of st of Neyman's the formula 1 divided by n summation, okay, I runs from 1 to n of pi of si minus s bar whole square. So which is also be the some positive quantity and added to the right hand side to make it it as equal. Then so which one is greater here? Variance of y bar of r is always greater than. So variance of y bar of st of the Neyman's is always less than or equals to the 3. Put it as equation number 3. So from 1 to 3 we can say that variance of y bar of r is always greater than or equals to variance of y bar of st with the proportionality is greater than or equals to variance of y bar of st of Neyman's. So hence this theorem is proved. So very important theorem for the BSc final years and semester 5. Okay, thank you.